Today I'm going to talk about handling allowable limits for recovery, and I've said that's a puzzle because we're still developing the Eurachem guidance, and we have if you like, some debate about how to handle permitted limits. So there's a little bit of speculation here at the moment. So I'm basically describing where my thinking is at the moment, and it'll be interesting to see whether other people agree. So I'm going to talk a little bit about where these limits come from. I'm then going to talk about how we normally handle limits in measurement uncertainty, because that's the background to the discussion. And then I'm going to talk about whether analytical recovery measured at validation, or analytical bias, which is just another, well, recovery is a special case of bias, whether that's just another input quantity. And then talk a little bit about when permitted limits should or should not contribute to measurement uncertainty. So let's move on there. This is a typical example of where limits come from. This is the UK performance standard for laboratories doing soil testing. It's an MCerts standard, so it goes along with a large set of documents that govern testing for soil, particularly for contaminated land. And if you open this document, you find that there are tables inside, and if you look closely at those tables, you find that there are specifications for precision and bias. And the idea is that there's a validation procedure that's included in the MCerts standard. Laboratories go through the validation process and they test whether the bias is within those limits. So this one effectively says you're allowed a recovery of 100 plus or minus 15%, say for antimony, a bit wider for boron. So the regulator has set limits, and if you're within those limits, you're allowed to use that test method. Of course, being an environmental standard, there's limits for organic contaminants as well. They're a bit wider because they're a little bit more difficult, but another very commonly cited example is the European series of guidance and regulations for pesticides. Same kind of picture here. We have a list of requirements for mean recovery. This particular one is couched in terms of recovery rather than bias. The only particular feature about this one is that these are asymmetric, but we've still got a list of permitted recoveries. And if laboratories find that their recovery at validation is anywhere in that range, then they are permitted to proceed. And there are a couple of provisions in this guide for correction when the recovery is extreme but within the permitted range. But in general, the system is a permitted range here, in this case 70 to 110, for example, for at low levels. So going back to who sets the limits, mostly it seems to be regulators where we see this, and they typically set limits for validation so that there has to be acceptable recovery found at validation. Some of the standards, and I believe the pesticide standards are among them, set limits for regular spike recovery as a quality control check during an analytical run. You do one spike recovery, check whether that's within the permitted range, and that allows you to proceed. And that's over and above any quality control that you might have in place yourself. Laboratories, of course, can set voluntary limits or QC limits themselves, but typically the ones we're most concerned about is the ones set by regulators. All right, we've got limits for something. We've got permitted limits. We know that laboratories that pass these checks will be undertaking measurements. Now, in other contexts, limits are quite common in measurement uncertainty. And I'm going to use the example of glassware. We have glassware that's typically a particular class. In this particular case, a 10 milliliter class A volumetric flask has a manufacturer's specification of 10 plus or minus 0.02 milliliters. We normally treat that by assuming a distribution. It might be rectangular, which is quite conservative. It happens that the GUM suggests a triangular distribution for glassware. If you wanted to be conservative, you could assume a rectangular distribution, but once you've assumed this distribution, there's a formula that goes with it, and for a triangular distribution, this is the formula. We can get a standard uncertainty from the specification. So our standard uncertainty that we would associate with a volumetric measurement is straight out of the GUM. So that's when you've got a straightforward specification. Now, that may or may not have been measured. Let's have a quick look at where that might have come from. If you're producing glassware or some other components, for example, electrical resistors, a fairly common way of producing graded products is to produce a large number of products as well as you can. And let's say that we're able to produce glassware quite reliably within plus or minus 0.03 without trying very hard. And then we apply a quality control check. And things that pass the quality control check get marked Class A. And you might, for example, if you had several thousand, in this case, flasks, you might decide that you need 500 for sale at Class A and more for sale at Class B. So the first 500 that pass Class A are sold as Class A, and any that didn't, and any that you haven't yet tested, get marked as Class B. And that gives us glassware where the manufacturer can be sure that they're within plus or minus 0.02. Now, that's a manufacturing process. What does it look like in method validation? Well, it looks much the same from the outside. We have a lot of standard operating procedures. We put those through a recovery check. Everybody checks their own SOP, puts them through a recovery check, and the ones that pass the recovery check are the methods that end up in use. Methods that don't pass typically will be amended and put through the process again. Now, on the face of it, that looks exactly like our manufacturing problem. So perhaps we've set an allowable recovery of 100 plus or minus 20%. If we chose exactly the same logic, well, we know our recovery is within 100 plus or minus 20%. We don't know where, so I've gone for a somewhat wider distribution, a rectangular. And the standard uncertainty is, again, the allowable deviation divided by √3. And that gives us, for this particular system, about 11% standard uncertainty. So that looks quite reasonable by comparison with typical components, other input quantities. And the question I'd like to ask is, well, is that actually reasonable? Should we be treating permitted recovery in exactly the same way as a manufacturer's specification? There are some things I think that we need to think about. The first question I have is what this distribution describes. And there are two obvious possibilities. One is it's a description of the uncertainty about recovery for a particular standard operating procedure or laboratory. That's how we treat the glassware uncertainty. The other is that it's the spread of recoveries that a regulator can expect to see across a large number of laboratories. So if we did an inter-laboratory study, we might see that range of recoveries. Now, from what I've described, it's perhaps more accurate to look at this particular way of looking at things. That is, we're looking at the range of recoveries the regulator might see if they took a random sample of laboratories rather than the uncertainty for a particular laboratory. And the reason for that is partly that from the laboratory's perspective, the laboratory has already estimated their recovery. They did a recovery check during method validation. They know roughly what it is. They might also be doing it regularly for quality control. And that means that each laboratory has more information about recovery than is provided by just reading the permitted limits. And we also know something about how to use laboratory estimates of recovery in measurement uncertainty evaluation. So it looks like laboratories are not in the position of having only the permitted limits to rely on. They've got their own information, and they could in principle use that for uncertainty associated with recovery or bias. I'm going to try something now. I'll be interested in understanding what everybody thinks in the meeting. So I'm going to launch a short poll just to find out what happens. What do you think is the best way of handling regulatory permitted limits when you're thinking about measurement uncertainty? And the options are relatively straightforward. The first one is use the regulatory range in estimating the uncertainty. The next is use the laboratory's own information. A third is another possibility. We can say it was a quality control check. If you're okay, don't do anything new. Just regard the quality control check as passed and don't make anything else. And another possibility is that there might be something else. So I'd like you to, you should be seeing a poll. If you can just pick the action you think is most appropriate, then I'd quite like to see what we get back in terms of responses. I think that's about it. We peaked out at 75, and that's interesting because as you can see, the vast majority of people who've responded think that the most appropriate thing is to use the laboratory's measured recovery. And that's interesting because we can consider that in developing ongoing bias. Let me move on and talk about quality control very briefly. Quality control may or may not be a different case. If you imagine the same kind of situation, every analytical run, we run a check sample with perhaps a spike recovery, and we get a recovery. We have some limits. We check that against the regulatory permitted limits, and if it passes, we are allowed to continue. We don't have to do anything. There's no action to take. Now, if we did that over a long period of time, that has an interesting effect on the spread of results that we might see. If we have very narrow permitted, if we test very stringently for recovery, we test positively to make sure that the recovery is inside the permitted limits. We get a relatively narrow distribution of analytical results. If we then do look at the analytical results we might get from that run, as we change to a situation where any recovery that doesn't significantly exceed the allowance is permitted, we see that the distribution spreads. So not surprisingly, as we widen the QC criteria, assuming that the process would otherwise generate quite a wide range of values, precision gets noticeably poorer and their shape actually heads towards something rectangular if we got a very simple plus or minus 10%, for example. Now, usually, poorer precision does mean larger uncertainty. If we saw 5% precision, we'd have a standard uncertainty of 5% for random effects. If we saw 10% precision, we'd put in a precision component of uncertainty of 10%. So we can see that including some kind of permitted limits that are over and above our normal precision control limits, they're not statistical process control, they're regulatory permission. So they're like to be wider than the statistical process control limits. We can see that that could, in principle, increase the dispersion, reduce the precision, and that means larger uncertainty. The moderating factor there is that if we have included those limits in our method validation studies, we would hope that that degradation in precision that we might see is reflected in our intermediate precision. So if we've got large QC limits that we're using during our intermediate precision studies, we should see a larger precision component anyway. And that means maybe we do not need any further action if we've done our precision studies correctly, including the limits. So I've got another poll here, which is much the same, to see whether you think the same about quality control. Again, what do you think is the most sensible treatment of permitted limits for recovery if they're used in quality control instead of at validation? Does it make a difference? Okay, we seem to have peaked out. That's interesting that looking at the poll results so far, it's more balanced, that in the quality control circumstance, it looks like the permitted range might actually be a more acceptable thing to consider. Well, let me wrap up and thank you for the feedback there. So I did put some conclusions on this talk, but they had a question mark on the end because I was genuinely interested in what everybody had to say. So this is what I thought before we did the polls. Recovery at validation looks like primarily a quality assurance check to make sure that the method has sufficient performance. And the permitted range is just to make sure it does. But because the laboratories have got information on recovery, it seems quite sensible to use their measured recovery in evaluating measurement uncertainty. The permitted limits then don't have any particular influence on that. So we don't need to use the permitted range for uncertainty. And I'm pleased to say that that coincides with what the earlier poll said. Turning to quality control, it's a bit more of a balanced picture. We may have allowed for our quality control limits in determining our precision anyway. If that's the case, we shouldn't need to take any further action. If there's a reason that we haven't, for example, we've got a very consistent test sample that we've been using for recovery checks, and we're concerned that it might change over matrices or perhaps over analytes if you're doing something like pesticide studies where you've got 130 analytes you're monitoring for. They can't all be tested and they won't all be in. Then perhaps the permitted range is a useful proxy or something that you could add. So there's a maybe there. And I think there is a possible case where regulatory limits for recovery might be relevant, and that's when there is literally no other relevant available information. So if you're a regulator with a measurement result in front of you that hasn't come with an uncertainty, perhaps that's a good time to say, well, we've allowed them to report anything between 70 and 110%. I should bear that in mind when I'm making decisions. And that's where I'm going to stop. So thank you very much for your time and attention. And I'm going to hand back to Michaela for any questions.